Hello and welcome to this simulation. Today I'm going to do a model of the compression test, dynamic compression test of the concrete column reinforced with CFRP bars. My min is this here. This is the column and this is the front view of the column, and we have 4 or more CFRP bars inside the concrete. So I'm going to use solid part for 2 CFRP and concrete parts. So let me click here. Name is column 3D deformable solid extrusion, approximate size ½ meter, and continue. Create a rectangle. The first point -0.1 and -0.1, 0.1 and 0.1. This is a square with 20 centimeter length. Now let's move to create 2 center line here. This is the first, this is the second. Use fixed constraint to constrain them. And now create a circle. This is the CFRP. This is CFRP, and the radius of the CFRP is 8 millimeter for instance. And this distance is 5 centimeter, okay. This is 5, again, okay. And now click on linear pattern to copy this. Select it, done. 10 centimeter 2, 10 centimeter 2. It is okay now. So double mid click. The depth is 1.2 or more than 2 meters, 3 meter. Okay, this is a short column. Now the CFRP, again it is 3D deformable solid extrusion. Usually we use the shell or continuum shell to model the CFRP, but here I'm going to use solid part and solid element to model it. So continue. Click on a circle, the center 0 and 0, press enter or mid click, 0 and 0.008. This is the radius. Okay, double mid click, 1.2. This is the depth. Okay, go to assembly, enter 2 parts dependent. Okay, now translate this part, done. This point to here. Now use linear pattern, select the CFRP, done. It is 10 centimeter, it is 10, rotate, flip it, and now the direction is okay. So now click on replace selected, select the cell, select this, and done. Create 4 surfaces for the concrete to consider the constraint, tie constraint between the concrete and the CFRP. We can assume another part as a cohesive part between these 2 parts, but it will be better if we use tie constraint. So create a surface, name is C1. This is the surface. The second surface C2. The third surface C3, and the last surface of the concrete is C4. Okay, and now add all, remove selected, remove the concrete. Okay, create FRP1. This is FRP2. This is FRP3. This, and the last one FRP4. This. Okay, now go back to part, create another part, rigid part. It is discrete rigid, shell, planar, and continue. Create a rectangle. negative 0.15 and negative 0.15. This is the first point, mid click, 0.15 and 0.15. This is the second point, double mid click. This is the hydraulic jack, and this is the boundary zone. And create a reference point at 0 and 0 and 0 to control this plate. This is the control point. And now go back to assembly, enter the rigid. It is okay, just copy it, create a copy of this. It is 1.2, this is a distance, this is 1, and the direction is this, and that's okay. Now translate all the part done along the third direction. The first point 0, second point negative 6, 0.6, 60 centimeter, and this is the right position of the column. And let's create a set, name is reference point, to request the reaction force along the third direction and displacement for this point. So go back here. For the material, we know for concrete we have sigma C compression and sigma T in tensile. This is epsilon C and this is epsilon T, the strain. So the compression is something like that. It is. This is the maximum. This is sigma UC, and this is the failure strain. And for the tension, it is something like that. Something like that. It is failure here. This is the maximum. And also for the CFRP, we know that the CFRP is a different material. You know, in 3 direction, it has different behavior in X, Y, zeta, and the normal direction is the main direction. Okay, let's make it down, save it. I have the material in my library. And first CFRP, the second one is concrete with 30 megapascal compressive behavior. Okay, let's go to check first CFRP. Let's go to rename it CFRP. Edit it. We don't need Hashing damage criteria. The density is 1,800 kilogram per meter cube, and the elasticity should be engineering constant. We can use also the lamina if we use a shell, but here this is a solid part, so the engineering constant is okay. So this is the 3 Young modulus in 3 direction, post angulation in 3 plane, and also shear modulus. Okay. And for concrete, edit the density 2415 kilograms per meter cube, elasticity 23 gigapascal, post angulation 0.2, and the plasticity concrete damage plasticity, dilation angle, eccentricity, below stress ratio, shape factor, and viscosity. And now the compressive behavior. This is a compressive behavior. This is the diagram which I draw just a minute ago. And compression damage here. This is a compression damage. And the tensile behavior here. You can change the data. It is arbitrary. You can change the data based on your model. So now create 2 sections. The first section is CFRP section, solid homogeneous material, CFRP, and assign the material to this. Okay, and now the concrete, solid material concrete, assign it to this part. Now go to assembly. So the assembly is okay. The step. So the step, you can use a static step, but the static step is too slow, and I'm going to use explicit. The explicit has a little difference, maybe 10%. So here dynamic explicit, continue the time. If you can, use 1 second for the time, but here for instance 0.04. But if you can, use 1 second. And also the mass scale, use mass scale, create to E-6, 2 microsecond. This is a time target. The mass scale uh, can has effect over the dynamic explicit step to make it like quasi-static by increasing the imaginary density, and also it reduces the time of the simulation. Okay, done. Output 100 interval, for instance. Remove Eulerian request, we don't need them. Just failure, compressive damage, tensile damage, stiffness degradation for concrete, and status, and done. This is the outputs. And for the history output, remove the energy, select the set, RP 500, displacement along zeta direction, reaction force also zeta direction. Okay, now go to interaction. We can create the general contact to consider all contacts in the contact domain. So click on interaction, create general contact in a step initial. The property of this contact is a friction. Click on this contact, type contact, continue, mechanical, tangential behavior, and penalty 0.1 for instance. Okay, and now all contacts will consider during the analysis, but we know the contact between the CFRP bars and concrete is tie constraint. We can use surface to surface also, but here let me use to make it more simple. Use tie constraint, but also you can use surface to surface with cohesive behavior. So tie constraint between the surface, the master is concrete, the slave is this. Continue. Okay, again, master C2, F2 is a slave, again C3 with F3, C4 with F4. Done. And these are the constraints, and you can see these are the bar with tie constraint. Okay, now go to a step, sorry for that, the load. Click here, create boundary. In a step initial, displacement, continue. For this set RP, restrain it in all the direction. Now create another symmetry in Castor. Okay, this point, this is a ground, so it is in Castor. This is ground. So this plate is a hydraulic jack and it has moved during the analysis. So edit it. For instance, along zeta direction, -4 mm with a smooth amplitude. 0 is 0, 0.015 is 1. This is a time step and this is a magnitude. If you use 1 second, use 1 here instead this, and done, and okay, and this is the direction of the displacement. So the mesh for the CFRP 35, mesh it, it is good, and the element type explicit, element dilation yes, and okay. For this, let's me to use some partitions to have a better mesh. Partitions, cell, define cutting, point normal. This is point, this is normal, create partition. Select here, done, point normal. This is point, this is normal, create partition. Now select all, done, point normal. This is point, this is normal. Again, select all, done, point normal. This is point, this is normal. And I'm going to use 1 centimeter for the mesh. So mesh it. So it is too bad. Let's me to use sweep. It is better. Mesh it. That's good. So the element type for this is explicit. Element deletion, yes and okay. And for the rigid, it is good. Mesh part, the yes. Element type is explicit, discrete, rigid. So it is okay, and go to job, create a job, job 1 or any other name, okay, and submit it. So already I did it with 0.01 second as a time step, and I got the failure, and Abaqus got an error from my simulation because some element failed, and the Abaqus can't calculate more than that. So we forgot something here. See that this arrow, go back to material. It is related to the CFRP. The direction, assign material orientation. Select this part, done. Use default. Use discrete. The surface which we have a stack. This is the surface, done. And the edge is this, and we use edge direction, and you can see the axis 3 is normal in all the direction. Okay, so now job, submit. Okay, monitor. This is the anisotropic material. We need to assign direction to it. It is a circle, and the normal in each node should be on the outer surface of the cylinder, and we created that just a minute ago, the normal direction. If you got error because of the excessive distortion, don't worry. Your model failed and you achieved the failure point for that. So it is okay, you can see that. Let's try to kill it and save it for you as model 2. This is model 2, and already I did model 1. See the time step is 0.01 second. The mesh is the same. The job, see that distortion happened in this time, more than half of the time. So let's me to check the result for it, and let's me to use viewport annotation. Use 8 for this, and let's me to remove these texts here. Okay, and now let's just me hold the concrete. So click on this, and let's me to use magnitude to have a better view 10. See the failure happen here. See this deformation here. You can see that. See, this is a failure. And let's me to use feature edge to have a better view. See, and we can see the compressive damage. See the compressive damage 100% happen here. See that? You can see. And let's me to check the tensile damage. No, the tensile damage here. See the tensile damage. It is also the maximum value which we used. And stiffness degradation. This is the stiffness degradation, and we can see the animate here. See, okay, and let's me to use stress. And now the CFRP box. This is the CFRP. see the deformation for this. This is a CFRP, displacement, or everything. And let's me to check the plastic strain. See the plastic strain happen here. This is the failure. You can see it is completely fractured, or it is failed completely here in this plane. Now let's me to create a history output. The name is RF save as. Sorry for that. Again, save as this. Name is reaction force. Okay. And for this use displacement. Okay. And now in this use operate. Continue, combine, negative U, RF also is negative, plot it. Okay, see? This is the diagram. This is the increase in the force capacity till the maximum. It is around 1.1 meganewton. And after that, the failure happens and it reaches the zero value for the force. You can do that here with static till here, till this point. After that, the static can predict, and this is the dynamic can predict this. Okay, and this is the simulation, and you can change everything, the material, the dimensions, the everything which you want. And this is the mesh form. See. And also change the time step. The time step is so important. Use a bigger time step for the simulation to have a quasi-static model. Thank you for attention.